The impact of spatial skills training on success, value, and efficacy in introductory geology and biology courses. Research has shown for many years that STEM majors have very high attrition rates compared to other college majors. Approximately 60% of freshmen who declare a STEM major will change their major before they graduate or not graduate at all. A significant body of research shows that proficiency in spatial skills are correlated to greater success in STEM fields. So this leads to the research problem. Does intentional training in spatial skills increase success, value, and efficacy of biology and geology? STEM instructors tend to assume that spatial skills develop in STEM students organically without any intentional practice. Currently, spatial skills are not explicitly taught in undergraduate STEM courses. Before we talk about the design of this study, we should clarify what spatial skills specifically are. So spatial skills are composed of three broad groups of skills. The first is mental rotation, the ability to envision sides of an object that are not visible from the view the observer is given. So when we look at a three-dimensional object, predicting what non-visible sides will look like. Disembedding is the ability to find patterns in visual information when part of the pattern is missing or obscured. And penetrative thinking is the ability to envision the interior of an object based on the exterior features. There are clearly some gaps in the body of knowledge about the relationship between spatial skills and success in geology and biology and STEM in general. So the gaps in research lead us to 6 research questions that will be addressed with the current research project. First, we want to know if increased proficiency in spatial skills will be correlated to geology and biology students earning higher exam grades on exams in those courses. We'd also like to know if greater proficiency in spatial skills leads students to persist in STEM majors as compared to students who have lower proficiency in spatial skills. We'd like to investigate if students who are explicitly trained in spatial skills during the first half of the semester of an introductory geology or biology course ultimately show more positive changes in exam scores over the course of the semester as compared to students who are not trained in spatial skills. We'd like to know the impact of proficiency in spatial skills on students' perceived value of biology or geology. We'd like to investigate any correlation between proficiency in spatial skills and students' self-efficacy. Are students able to self-assess their own proficiency in spatial skills? Do they know when they're getting an answer right or wrong when asked a spatial skills question? And finally, we'd like to look at whether online or in-person instruction in spatial skills leads to more positive benefits to students. So this research study will have 2 treatment groups. We'll have a group of students who are participating in online instruction of spatial skills and a separate group who are participating in in-person instruction of spatial skills. We'll also have a control group. That group will be receiving in-person instruction in STEM career options. We'll be measuring 4 dependent variables. First, we'd like to simply know the proficiency that students have in spatial skills. This will be measured with a commercially available spatial skills test. We'd like to know students' success in biology or geology and STEM in general. So this will be measured by students' exam grades in those introductory biology or geology courses, and by students' declared major 6 semesters post the initial data collection period. Next, we'd like to measure the value that students perceive their biology or geology courses to have. So what value does their introductory biology or geology course have to their future coursework or intended career? And finally, we'd like to investigate whether students are able to recognize their own proficiency in spatial skills tasks. We'd like to measure students' self-efficacy. We have several hypotheses. First, we expect that students who get explicit instruction in spatial skills will have a greater proficiency in spatial skills after that training is complete. We expect students who have greater proficiency in spatial skills will also have higher exam grades in their introductory biology or geology course. We expect higher proficiency in spatial skills to be correlated with an increased perceived value in biology or geology. Next, we believe that participation in spatial skills training will be correlated to increased self-efficacy when the students take a spatial skills test after completing spatial skills training. And finally, in comparing in-person training to online training modules, we expect the in-person training to have a greater effect than the online training. For this research, we'll be working with undergraduates who are enrolled in Biology 101 or Geology 101, the introductory courses, which each contain a full semester lab component. And we'll be focusing on students who are enrolled at a large research-focused university. We'll be focusing on students who are at the beginning of their college career. So students who have 25 credits of college coursework or greater at the course of the semester, their data will not be recorded. They'll participate along with their classmates, but we won't record their data. For research design, during the first week of classes, students will complete a pretest of their spatial skills. Again, this is a commercially available spatial skills test. And this test will include, after each question about a spatial skills problem, a question where students will rate how confident they are in their answer, and that will serve as the efficacy component. We'll also ask demographic information, including their intended major, but also age, race, number of college credits completed, and other general demographic information. We'll also ask students to complete a survey, Likert-style survey, where students evaluate their perceived value of the geology or biology course that they're enrolled in. During the first 6 weeks of the semester, students will participate either in online instruction or in-person instruction in spatial skills if they're part of those treatment groups, or in in-person instruction regarding STEM career options. Entire lab classes, typically 24 students per lab section, will be randomly assigned to one of the 3 treatment groups. Exam grades over the course of the semester, the 4 semester exams, those grades will be collected. During finals week, students will complete a post-test of their spatial skills, and as with the pretest, the efficacy questions will be included there. They'll also complete the Likert-style geology or biology value survey, and they will tell their intended major. Then, 6 semesters after the initial data collection semester, the researchers will work with the registrar's office to find the declared major at that point for each of the students who was in the introductory course. A couple minor ethical concerns here. Of course, we want to do everything with high ethical standards. We need to make sure to keep the data anonymous. That way we aren't using anyone's data inappropriately or violating any FERPA provisions. Also, there may be some minor concern about asking students to complete a task, specifically in the spatial skills training or the control group doing the career options training. These tasks won't necessarily be directly correlated to the student's course grade, so that could be a concern as well. Informed consent from all participants will be gathered at the beginning of the semester before any data is collected. Finally, a brief reflection on completing this project. This is clearly a quantitative research project, and while qualitative research has value in its depth and nuanced data collected, the quantitative approach is much more appropriate in this case because we'll be able to talk about statistical significance between the different treatment groups, and that will make a much more strong case for recommending universities change the course offerings for STEM students. Considering the alignment of the research purpose and the research questions is essential in conducting good educational research. However, this is fairly intuitive. Double checking and triple checking to make sure that the independent and dependent variables are closely related to the questions being asked, and then all the way back to the research purpose is important. And finally, this working process has given me some very valuable practice in intentionally designing a research experiment that produces high quality data that could be publishable and ultimately have the potential to change in a positive way some small aspect of undergraduate STEM education.